Hello friends, we are Group 4 and we will be presenting our project on enhancing sustainable energy system with reinforcement learning. My group consists of Benjamin Chin Wei Hao, Cha Xiu Xiang, Chao Teng Cheng, and me, Henki Liang. And without wasting any time, let's get right into the topic. There are 6 main sections that we'll be covering in our presentation, including introduction, problem formulation, methods, framework and experiment, future work, and finally the conclusion. First, I'll give you a brief introduction to our project. In this project, we apply reinforcement learning to enhance sustainable energy systems in a simulated environment. The simulated environment is created using the building EMV from the SustainGym package. It is a simulation framework designed to replicate real-world building energy dynamics. The objective of the real-world function in the environment is to reduce energy consumption while maintaining a comfortable temperature range. And additionally, the state in the environment is fully observable, eliminating the need to model latent states like stochastic latent actor critics, SLAC, or to model partially observable Markov decision process, PMODP. Next, we'll be moving on to the problem formulation. Our objective is to compare the performance of reinforcement learning agents trained using 2 distinct approaches, deterministic and stochastic. For the stochastic models, we will implement proximal policy optimization, PPO, proposed by Schulman et al. In 2017, and soft actor critic, SAC, proposed by Hanoja et al. In 2018. These methods excel in environments with uncertainty. And for the deterministic approach, we will use twin delayed deep deterministic policy gradient, known as DD3, proposed by Fujimoto et al. In 2018. It is known for its stability and precision in fully observable environments. And for the building environment, we'll be focusing on an office small building size with the average ground temperature of Tucson under the weather condition of hot and dry. And that is all for my part. I'll now pass the time to Benjamin.
Thank you, Kilian. My name is Benjamin Chin. So today I'll be discussing on the methods on how to manipulate the environment and also the frameworks and experiments conducted. So let's get started. So the environment we use in this experiment is a building environment from SustainGym, and it as introduced by the Kilian in the previous section. And the action space in the environment is between -1 and 1, which is after the scaling, and it controls the heating supply to 6 of the zones inside the office building. So the observation space is the 6 zones temperature and other 4 factors, such as the heat acquisition from the occupant activities, ground and external temperatures, and also the heat gain due to solar irradiance. And the environment consists of, it is 1 episode equals to 1 day, which is 288 time steps for the agent to learn. So the first modification applied to the environment is update the observation space lower bounds for the heat acquisition for the occupant activity to prevent out of bound state, which is set to 0 as shown on the figure below. The second modification is we adjusted the heat calculation using the US Department of Energy formula shown on the figure on the right side. So now I'll be discussing on the frameworks and experiment. So the first stochastic model used is the soft actor critic, or SAC, is of policy actor critic methods, and it consists of the stochastic policy with entropy maximization, which is used for exploration, and the stochastic model outputs probability distribution of all possible action, and it also uses 2Q function to mitigate the positive bias in the critics network. And it also uses the replay buffer for all policy training, where the agent will sample the experiences in the replay buffer to learn, and the value networks to reduce the variance due to the high fluctuation of the rewards throughout the experiment. So for the model training of SAC, it is trained for 1,500 episodes due to the computational complexity and also computational power to maintain 3 networks together. And the network configuration used is 256 hidden neurons in all actor, critic, and value networks. And the learning rate for all networks are set to 3 times 10 to the power of -4, and the tau are set to 0.005 to prevent the rapid changes of the target values for soft updates. And if you want to apply hard updates, you can set it to 1. So for the reward scaling, it is set to the factor of 2 to balance the trade-off between the exploration and exploitation in the entropy term inside within the reward function. So the next is the deterministic model, which is called the twin delay deep deterministic policy gradient method, and is an off-policy integrating method. So it's used to train the deterministic policy where the agents only outputs one action, and it consists of a double Q value function to reduce the overestimation bias by the critics networks. And it also used the target policy smoothing and delay updates to ensure the actor receive the more accurate estimated Q values. The modification we applied to this TD3 is we double the hidden neuron in the linear layer of Q networks, and we adjusted the policy noise and clip values for stability, which the effect will be shown on the result part. So for the model training of a TD3, the default configuration stated in the paper is 256 hidden neurons and the policy noise of 0.2 and the noise clip of 0.5. And we modified the configuration by increase the number of hidden neurons to 512 in the linear layer for all the networks, and also to reduce the policy noise and the clip noise to 0.1 and 0.2 respectively. So here is the results of the SSE and TD3. So for the SSE, we can see that the score fluctuates more at the beginning of the learning process of the agent compared to the end of the learning process of the agent, which show the exploration and exploitation by the entropy term and also the reward scaling factor. And it's seen that the policy or the agent are converged towards the optimal policy at the end of the learning process, which is almost the horizontal line. So for the TD3, before hyperparameter tuning, you can see that the graph are quite noisy, which is it shows the average rewards over 10 episodes, which means that the agents are unable to learn the gradients for the policy improvement process. And for the TD3, after tuning, which is we lower the policy noise and also the noise clip, it is more stable throughout the learning process, and it achieves the trade-off, optimal trade-off between the energy consumption and the temperature of every zones at the end of the learning process, which shown on at the end of the graph. And the maximum average reward over 10 episodes achieved by the TD3 after tuning was around negative 100, which is quite close to 0 compared to SSC, where the maximum average reward over 10 episodes was around negative 800. So let's welcome Xiu Xiang to discuss on the proximal policy optimization method. Thank you.
Thank you, Benjamin, for his presentation. So now I will present the model I used in this project. The model I use is Proximal Policy Optimization, PPO. PPO is an on-policy gradient method and known for its stability and efficiency. It directly estimates a stochastic policy by utilizing a value function critic to estimate the value of the policy. Furthermore, it also has clip server grade objective function to enhance training stability by limiting the size of the policy change at each step. There is a hyperparameter was tuned in this project, which is learning rate, step per update, batch size, and total time step. The learning rate was tuned by using genetic algorithm, and the step per update is set to 288, which used to simulate 1 day, and the batch size was set to 64, and the total time step is set to 2 millions. Next, we focus on the model training process. The PPO was trained by using the stable baseline package, and it trained for 2 million time steps using genetic algorithm tuned learning rates. After that, we monitor metrics such as cumulative reward and training stability to evaluate the performance. The learning rate was tuned by genetic algorithm. Therefore, the space of stretching of learning rate is set to 0.0001 and to 0.01. The population size of genetic algorithm was set to 5 over 3 generations, and the fitness evaluation was based on mean reward over 3 episodes of the 50,000 time steps. This is a result of the output of genetic algorithm. Therefore, we can know that the best learning rate is 0.0009. Therefore, this learning rate will set to the learning rate of the model. Finally, the results show the performance of PPO. Unfortunately, despite optimizing the learning rate with genetic algorithm, the reward fails to converge to a higher values. The graph displays cumulative reward versus episode count, showing significant variability without a clear trend toward improvement. This suggests that further optimization or adjustment in the approach may be required. And this is the end of my part. I will pass the presentation to Teng Cheng. Thank you.
Thank you, Su Xiang. My name is Teng Cheng, and I will continue with conclusion. So, among these three approaches, TD3 demonstrated the best performance, showcasing stable learning and achieving an optimal balance between energy consumption and maintaining comfort temperature. Its deterministic nature and targeted hyperparameter tuning played a significant role in this success. SAC, on the other hand, excellence in balancing exploration and exploitation, thanks to its reward scaling and entropy-based approach. It is a strong candidate for environments requiring dynamic adaptability through its computational demands are higher. PPO, despite its efficient clip objective function, struggled to converge to higher rewards. This could be attributed to limited hyperparameter tuning, indicating potential for further optimization. In the real world, this study illustrates how reinforcement learning can revolutionize sustainable energy system. It provides a practical framework for optimizing energy efficiency in buildings while maintaining comfort. This approach can guide decision makers in selecting reinforcement learning models tailored to their specific computational resources and goals, advancing sustainability efforts across diverse applications. Now, for future work, hyperparameter tuning, exploring methods like Bayesian optimization could significantly enhance the efficiency and effectiveness of our models. By automating and refining the search process, we can identify more optimal configurations for both PPO and TD3. Ensemble learning, combining the strengths of multiple models such as PPO and TD3 through techniques like weighted averaging or stacking could lead to improved robustness and decision making. This approach ensures that each model advantages are leveraged, making the system more resilient in dynamic and unpredictable environments. In summary, these future advancements hold the potential to not only refine the current methodology, but also expand its applicability to broader sustainability challenges. That's all from me for now. Thank you.